You may find it strange, as I certainly do, that there are so many models for the activity coefficients in modeling the phase equilibrium behavior for vapor-liquid systems. Up until this point in thermodynamics and phase equilibria, we've discussed 3 models at length, and also I've mentioned a couple more. So with all that in mind, we might ask the question of why are there so many models in the first place? And the answer to that question is that no single model can accurately predict all thermodynamic systems at all temperatures and pressures. Some models work best for some systems, while other models work best for others. With that in mind, you may be inspired one day to create your own thermodynamic model. When and if that happens, you might ask yourself, how do you know that the model that you created is right? And when I say right in this context, I mean, how do we know that it is thermodynamically consistent? That is what I mean by right in this context. And in order to evaluate the thermodynamical consistency, we need to evaluate the Gibbs-Duhem equation. So the Gibbs-Duhem equation is something that I first introduced way back in lecture 12, or in class 12. And when I introduced it there, I said it was a constraint equation that must be true for any model of experimental data. So first, I'm going to show how you can prove to yourself that the one-parameter Margulies constant, the one-parameter Margulies model, obeys the Gibbs-Duhem equation, and then we'll talk about how we know that experimental data that we measure are correct. So I'm just going to pause and copy in the Gibbs-Duhem equation from class 12. Okay, there it is, and this should look familiar. Remember that this theta is a stand-in, that's a variable that can be substituted for any thermodynamic property. So in the case of modeling activity coefficients, I'm going to substitute and say that theta is equal to excess Gibbs energy divided by RT. So applying that to the Gibbs-Duhem equation gives me the following expression. X1 d partial molar excess Gibbs energy over RT plus X2 d partial molar Gibbs energy over RT. And I need subscripts here for 1 and 2. Okay, and then the partial derivative of the partial molar Gibbs free energy, double partials, partial derivative of the partial Gibbs excess molar free energy. Yikes. Teaching phase equilibria is very, very difficult to keep everything, to say everything correctly at the same time as you're trying to write it. Minus dGe over RT with respect to pressure at constant T, X1, X2, dP is equal to 0. All right, now in order to evaluate the Gibbs-Duhem equation, I need to decide whether I want to do it for the PXY case, in which case temperature is constant, or the TXY case, in which case pressure is constant. And either way will get you to the same final answer, but evaluating the PXY case where temperature is constant is much, much simpler. That is because when you evaluate the PXY case, when temperature is constant, this third term, this partial derivative with respect to T, cancels, because dt is equal to 0 for PXY case. And that is at constant temperature. Now, if I were evaluating the TXY case, I would cancel the fourth term because there is no pressure change. And you'll see why in a moment, because when I cancel this one, I can also cancel this term on the logic that I've proved before in Monday's class. I didn't prove it by showing it directly, but I evaluated expressions for how this GE over RT term changes with respect to pressure. And then I said if you were to plug in actual values for it, you would see that there is not much change with respect to pressure. So logical basis here for this cancellation is that GE over RT is not a strong F of P. So if I change pressure a little bit, I don't expect the molar excess Gibbs free energy divided by RT to change much. Now again, in the other case where I'm doing the TXY, I couldn't necessarily cancel this third term. So it'd be a little bit more difficult mathematically, which is why I'm doing the PXY case. Again, it shouldn't matter either way. It's just in terms of which one is more complex. Now what I want to do is substitute in. I know what the partial molar excess Gibbs energy for component 1 is, I know that I can rewrite this as d ln of gamma 1, just by definition, and this is d ln of gamma 2. And then I have expressions for what those gammas are. So ln of gamma 1, you can also say, is this one. So I'm just going to rewrite the equation and substitute in as I go. So x1, the partial derivative of n GE over RT with respect to dn1 at constant t p and n2 plus x2 partial derivative of n GE over RT with respect to n2 at constant tp and n1 is equal to 0. And here, this is the constraint equation. So this is a convenient form of the Gibbs-Duhem equation to evaluate whether or not your activity coefficients are thermodynamically consistent. So at this point, now what we have to do is, I didn't actually have to do this step. This step is just showing you, I guess, another form of what the activity coefficients are. Since we're evaluating the one parameter Margulies expression, all we have to do is plug in our expressions for ln of gamma 1, which is a x2 squared, and ln of gamma 2, which is a x1 squared. So if we plug these expressions for our ln of gammas into the simplified Gibbs-Duhem equation, and we see that it works, we're able to conclude that the one parameter Margulies expression is indeed mathematically and thermodynamically consistent. So let's go ahead and do it. I'm going to substitute into this form of the equation now. So it's x1 times d. Oh, and I need to take the derivative with respect to something. So I need to take it with respect to x1. So take derivative with respect to x1. So I can't just evaluate d ln of gamma 1. So it's d a x2 square with respect to dx1 plus x2 d a x1 square with respect to dx1 is equal to 0. So does this jive? Does this make sense? All right, so in order to evaluate this derivative, I need to substitute in 1 minus x1 for x2. So do that here, 1 minus x1, and that's squared. So taking the derivative with respect to x1, it gives me, well, first of all, x1 stays out front. I've got a square that has to come out in the front, so 2, and then the inside derivative is a negative. So 2 minus 1, a, and then 1 minus x1. And then when I take the derivative, remember this exponent gets knocked down by 1, so it's to the first power. So this is a slightly longer way to do it. You can simplify in a moment. Plus x2, and this derivative is a little bit easier. It's a 2a x1. That's it. Equals 0. So do I have cancellation? I've got minus a to 1 minus x1. So most of this stuff should factor. Right? Or, oh, I know what I do. I know what I have to do. I have to say this x2 is 1 minus x1. And then that makes it really easy because I have the same thing on both sides. So this will cancel out and I get 0 is equal to 0. Which, because it works out, because it's 0 is equal to 0, this tells me that Gibbs-Duhem is satisfied. And the one parameter Margulies model is thermodynamically consistent. So once again, just to summarize this first half, thermodynamically consistent. One day when you make your very own model for the activity coefficient, it must pass this test. Otherwise, it's not going to work. So again, that's the test for a model. Next, we'll talk about how do we know that experimental data is right. And until now in phase equilibrium, I've been telling you that experimental data is always gospel. You should always follow experimental data if you have it. Yet it's not infallible, right? I'm sure, well, you haven't taken unit ops, and when you will take unit ops, you will see that sometimes you might get experimental data that doesn't make any sense. So for instance, say you have a simple mixing operation and you're able to measure the flow rates of two things going into a mixer and one thing coming out of a mixer. Say you measure the mass flow rate and you get 100 kilograms per hour in the first stream and 100 kilograms per hour in the second stream. That should equal 200 kilograms per hour, but say you measure all three streams and the third stream is 150 kilograms per hour. That would be an example of how you know something is off with one of your three measurements or more of the three measurements. You know that those measurements aren't correct because it doesn't match up with theory. And we know that the mass balance is something that absolutely cannot be broken. That is theory that is infallible. We must have mass in equaling mass out. And if we don't have mass in equaling mass out, that means there's either a problem with our measurements or there's a problem with our process. Maybe we're losing some in some unaccounted for way. So how do we go ahead and double check our experimental data? So you get something back from the lab. How would you go about and check that your experimental data is correct? And to evaluate this, we're also going to use the Gibbs-Duhem equation. So in video 17.2, I wrote the following equation. So I wrote excess molar Gibbs energy divided by RT is equal to x1 ln gamma 1 plus x2 ln gamma 2. So again, this is video 17.2. And don't do like I did and say, well, this looks exactly like the Gibbs-Duhem equation. And the Gibbs-Duhem equation, that this is a d ln of gamma and a d ln of gamma 2. So there is no d's there. And then this is why this is equal to molar Gibbs energy divided by RT instead of 0. So the data that you get from the lab will have to obey this equation, right? Because that's what the model also obeys. And if you know that the model obeys Gibbs-Duhem, then you have to know that this equation also is the same. So remember when I did that example problem, I evaluated what the experimental activity coefficients are. And we're going to say that that is the gamma with a star. So gamma 1 star is the experimental activity coefficient. This is what you get when you use Raoult's law and you say, so gamma 1 star for an instance would be y1p divided by x1 p star of 1, where y1 and x1 come from experiment. Then furthermore, you can use those experimental activity coefficients to obtain the experimental excess molar Gibbs free energy. So for the experiment, you can write the following. You can say GE star over RT. This is the experimentally determined excess molar Gibbs energy equals x1 ln of gamma 1 star plus x2 ln of gamma 2 star. All right, so this is all for the experimental. And now, just like we did for the model case, I'm going to take the entire derivative of this expression with respect to changing x1. So this is now d dx1 GE star over RT equals d dx1 of x1 ln of gamma 1 star plus x2, d dx1 of x2 ln of gamma star 2. And we also need to rewrite, we can't use x2 because it's a function of x1, and we know what that expression is. It's 1 minus x1. All right, so now we want to take the derivative of this expression. We have to use the chain rule now on the right-hand side because gamma is a function of x. So gamma 1 is f of x1. Remember, you saw that when I was doing Excel, right? As composition was changing, x1, or the activity coefficients were also changing as well. All right, so once again, let's chain rule both right-hand side terms. So to chain rule the first term, I got to take the derivative of the first multiplied by the regular second, and then I have to switch it. So the derivative of the first is a 1 times the regular second function. So 1 times ln of gamma 1 star plus take the first function normal, and then take the derivative of the second. Now, although I know that gamma 1 and gamma 1 star, for that matter, is a function of x, I don't know what the relationship is, so I can't evaluate what that integral is. But that doesn't turn out to be a huge issue. So I just say d dx1 ln of gamma 1 star. Plus, now for the second term, I have to take the derivative of the first, so that's a -1 times ln of gamma 2 star, and add plus 1 minus x1 d dx1 ln of gamma 2 star. And remember to keep the left-hand side in the equation. Now I say that if this experimental data obeys the Gibbs-Duhem equation, and I'm assuming that it does, and I'm going to evaluate this expression, and if it's not true, then that proves me wrong. But I say if that is true, then I have to know that this term plus this term must equal 0 by the Gibbs-Duhem equation. So x1 d dx1 ln gamma 1 star plus x2 d dx2 times gamma 2 star must equal 0 if Gibbs-Duhem is obeyed. And now I have to look at what I'm left with. So now in my equation, I've got d dx1 g e star over rt is equal to ln gamma 1 star minus ln gamma 2 star. And again, when I have a logarithm subtracted like this, I could say it's ln of gamma 1 star divided by gamma 2 star. And now I have a differential equation that I can separate variables and integrate. So dge over rt equals ln gamma 1 star divided by gamma 2 star dx1. Integrate both sides. I'm integrating with respect to x1. So from x1 is equal to 0 to x1 is equal to 1. And evaluating both sides. So this is a derivative of 0, which is just the function itself. So ge over rt evaluated at x is equal to 1 minus ge over rt evaluated at x is equal to 0 must be equal to the integral from x1 is equal to 0 to x1 is equal to 1 of a ratio of the activity coefficients. Now on the left-hand side, I know what the excess Gibbs energy divided by RT is for x is equal to 1. Because this is a pure component, I can get rid of this term. So GE over RT is equal to 0 for a pure component. And when x is equal to 1, I do have a pure component. Same thing when x is equal to 0. x1 is equal to 0. That means I have pure component too. So this term cancels as well. Therefore, we call this the integral test. So if, finally, I've got 0 is equal to the integral from x1 is equal to 0 to x1 is equal to 1, ratio of the experimental activity coefficients must be 0. So if you wanted to go ahead and test the experimental data that I gave you in that example problem the other day, all you do is you take the ratio of the experimental activity coefficients. So the steps are 1, plot gamma 1 star over gamma 2 star. Oh, sorry, I'm missing an ln here. I need that. I dropped that. Yep, dropped it there too. It's got to be ln. Plot ln versus x1 for range of x1 equals 0 to x1 equals 1. And then you should see that this function will cross the axis at some point. So at some point, gamma 1 star is equal to gamma 2 star. You should see that because they switch. One goes up while the other one goes down. And then you should be able to evaluate area under the curve. And if that area is equal to 0, in other words, if the area above the axis cancels with the area below the axis, then you have thermodynamic consistency. If area above curve, if area below curve above axis, below curve above axis equals area above curve below the axis, then data may be thermodynamically consistent. And this maybe is kind of troubling because we've gone through all this work and it doesn't tell you for sure whether or not your data is legit or not. It just tells you that it may be. So in other words, if it fails this test, you know that it's no good. Whereas if it passes this test, there's still a possibility that it might not be any good, but it's a good sign. Then data may be thermodynamically consistent. So I feel like this is a little bit convoluted of an explanation. Next class, not next video, because I have another example lined up for next video. Next class, I'll go through an example problem based on this that'll hopefully clear stuff up and tells you, again, try to give some context or some context to where you would actually use this stuff in real life. If you get data back from the lab and something's not working, you might want to try this integral test to see whether or not the data is consistent with what you're seeing. Once again, just to summarize, we're using the Gibbs-Duhem equation as a constraint equation that tests whether our model or our experimental data independently are thermodynamically consistent. That's all for this video.